Hi there, and welcome. Today we're going to talk about something truly foundational in computer science, something that actually explains how your computer understands, processes, and decides things. It's called formal languages and automata theory. Now don't worry, this isn't going to be heavy or mathematical. You don't need any background in advanced math. You just need to be curious and willing to follow along. We'll go step by step. By the end of the session, you'll not only understand the big picture, but also apply it to everyday tech, like search engines or even your code editor. Let's begin. Part 1. What is a formal language? Let's start with a simple question. If I give you a few symbols, say 0 and 1, and I ask you to build a few sequences, you might create things like 0, 1, 0, 1, 110, or 1001. These sequences are called strings, and the set of allowed symbols, in this case just 0 and 1, is called the alphabet.
Let's repeat that.
An alphabet is just a set of allowed symbols. A string is a sequence of those symbols. Now, here comes the most important part. We can define rules for which strings are okay and which ones are not. Let's say our rule is the string must start with 1. So now 1001 is valid, 011 is not, 1 is valid, 0 is not. We call this a formal language. Why? Because it's formal. It follows specific, well-defined rules. So in summary, a formal language is an alphabet plus a set of rules that define which strings are valid. Let's repeat that once more, slowly. A formal language is made up of an alphabet, strings built from that alphabet, and rules to decide which strings belong in the language. Great, let's keep going. Part 2. What is an automaton? Now that we have a language, how do we check if a string follows the rules? That's where we bring in an idea called an automaton. Don't let the word scare you. An automaton is simply a machine, not a physical machine, but a logical one that reads a string and decides if it's valid or not. Think of it like a gatekeeper. You give it a string, it checks the rules, and it either accepts it or rejects it. Let's take a quick example. Suppose our rule is only accept strings that start with 10. Now we want to check 100, yes, 10, 11, yes, 0, 11, no 1, no 0, no. We can draw a simple finite automaton, a kind of diagram, with states and arrows. Here's how it would work. Start at the first state. If the first symbol is 1, move to the next state. If the next symbol is 0, move to the final state. After that, accept anything, zeros or ones. So what does this machine do? It accepts any string that starts with 10 and rejects the rest. Let's say that again. The automaton reads a string and moves from state to state based on the input. If it reaches an accepting state, the string is valid. You've just met your first finite automaton. Part 3. Real-world example. Search engines. Now let's look at a real-world example. Let's say we're building a search engine, like Google. A user types in apple or banana and not orange. What's happening here? Well, this search query is actually a string made up of different symbols. Words like apple, banana, orange, operators like and, or, not, special symbols like parentheses. This is our alphabet, the basic building blocks. Now, not every string is valid. For example, something like an orange apple, not, doesn't follow the rules. So what do we need? We need a system to define what makes a query valid and a machine that can check it. This is where automata theory becomes powerful. We can define rules like parentheses must be balanced. Operators like and must appear between two valid search terms. A query must start with a keyword, not an operator. These are rules of the language. And to enforce those rules, we use an automaton to validate the query before running it. Now here's a new twist. If we're just checking whether a string starts or ends a certain way, a finite automaton is enough. But if we need to handle nested structures like parentheses inside parentheses, we need a more powerful machine called a pushdown automaton. Pushdown automata use a stack, like a memory helper, to keep track of things like open and close brackets. So once again, finite automata are good for simple patterns. Pushdown automata are used when we need to track nested or hierarchical structures. Let's say that one more time clearly. Use finite automata for flat regular patterns. Use pushdown automata for nested or recursive patterns like parentheses or function calls. Part 4. Why does this matter? You might be thinking, okay, this is interesting, but do I really need it for my job as a developer? Here's the answer. Yes, and here's why. Whenever you write code that processes user input, create custom parsers, design a chatbot or compiler, use regular expressions, or even build a basic form validator, you're already working with languages. And whether you realize it or not, you're also designing the rules for those languages. The better you understand how these rules work, the more robust your systems will be. You'll avoid errors, you'll prevent bugs, you'll design things that are easier to test and easier to scale, And that's what formal languages and automata theory help you do. Let's recap. Key takeaways. Let's go over the most important ideas we've learned today. A formal language is a set of valid strings built from an alphabet following specific rules. An automaton is a machine that checks whether a string follows the rules. Finite automata can check simple rules like starts with 10. Pushdown automata are needed for complex rules like matching parentheses. These concepts are used in things like search engines, code editors, and compilers. Activity. Apply what you've learned. Now it's your turn. Here's a simple task to help you internalize everything. Draw a diagram showing the relationship between an alphabet, strings, and a formal language. Pick 2 real-world systems you use, like a search engine or a text editor. For each system, write down what its alphabet is, the set of symbols it accepts, 2 or 3 rules that define valid strings or inputs. You can sketch it out on paper or use a digital whiteboard or notes app. If you like, you can even add colors to show transitions between states. Doing this will help solidify your understanding and give you a powerful tool to analyze any input system you build in the future. Wrap up. Thank you for following along. Remember, understanding formal languages and automata isn't just for exams. It helps you become a better thinker, a smarter designer, and a more effective developer. You now have the tools to look at any system and ask, what are the allowed symbols? What are the valid patterns? What kind of machine would I use to check those patterns? And that's the beginning of mastering computation itself. See you in the next session.